They are some of the strangest and most mysterious objects in our solar system, defying the traditional categories astronomers have long relied on to classify celestial bodies. Known as dark comets, these objects do not fit neatly into the definitions of either asteroids or comets, yet they exhibit properties of both. While asteroids are rocky, inert bodies that mainly reside in the asteroid belt between Mars and Jupiter, comets are icy and dusty, forming spectacular, elongated tails as they approach the Sun, often originating from the distant reaches of the solar system, such as the Kuiper Belt or Oort cloud. Dark comets, however, seem to exist in a gray area, appearing neither fully like a comet nor like an asteroid. Their peculiar nature has intrigued scientists, as these objects may represent an entirely new class of small solar system bodies, previously undetected due to their dim appearance, unusual behavior, and subtle activity. The study of dark comets is not just an academic curiosity. Understanding them could shed light on some of the most fundamental questions about the solar system's history, including the origin of water on Earth, the formation of planets, and the delivery of organic materials that may have helped set the stage for life. The first hints of these mysterious objects appeared in 2016, when astronomers observed a body that initially seemed to be an asteroid, but moved in a way characteristic of a comet. Ordinarily, asteroids follow predictable orbits and show no activity, whereas comets exhibit non-gravitational acceleration due to outgassing, the process by which ice and volatile substances vaporize near the Sun, producing jets of gas and dust that push the comet slightly in one direction, like natural thrusters. This 2016 object, however, exhibited small, measurable deviations from the trajectory expected under gravity alone, yet it showed no visible signs of outgassing, no dust trail, no coma, and no icy tail. Its motion, though subtle, could be detected by sensitive telescopes on Earth, and the unusual behavior raised questions about what forces could be acting upon it. These observations suggested that the small body might be releasing gas or particles in ways that are invisible to current telescopes, or that it might have a completely different mechanism driving its motion, challenging astronomers to rethink their classifications of solar system objects. The discovery of Oumuamua in 2017 further amplified the mystery surrounding dark comets. Oumuamua was an elongated, cigar-shaped object roughly 115 to 400 meters long, which also displayed non-gravitational acceleration but lacked the typical features of a comet, including any visible dust or ice emissions. Unlike the 2016 object, however, Oumuamua's trajectory revealed an astonishing truth. It was interstellar in origin. This made it the first known object to visit our solar system from another star system, a cosmic traveler that slingshot around the Sun before disappearing back into interstellar space. Its unusual shape, rapid rotation, and unexpected acceleration have sparked numerous debates among scientists, with hypotheses ranging from natural explanations involving gas emissions to more speculative ideas regarding its structure and origin. Oumuamua highlighted the diversity of objects that can enter the inner solar system and underscored that there may be many more bodies with unanticipated properties, both interstellar and native to our solar system, that we have yet to detect or understand. The scientific implications of dark comets are profound. If these bodies indeed contain water or organic molecules, they could provide critical insight into how Earth's oceans formed and how life-essential compounds were delivered to our planet. Comets have long been hypothesized as vehicles for transporting water and prebiotic materials across the solar system, but dark comets may represent an overlooked population that also contributed to this delivery process. Unlike traditional comets, with visible tails, dark comets' subtle activity makes them difficult to study from Earth, which means much of their potential role in shaping planetary environments could have gone unnoticed until now. Understanding their composition, whether primarily icy, rocky, metallic, or a complex hybrid, may help refine models of how small bodies evolve in the solar system, how they interact with solar radiation, and how their trajectories are influenced by forces beyond gravity. Adding to the excitement, a Japanese spacecraft is currently en route to study one of these mysterious objects, expected to arrive in 2031. This mission offers an unprecedented opportunity to directly investigate a dark comet up close. Spacecraft observations can reveal details that are impossible to capture from Earth, including surface composition, density, and any subtle outgassing activity that might account for the observed accelerations. Such data could finally answer lingering questions about how these bodies behave, whether their anomalous motion is caused by hidden sublimation, outgassing from tiny pockets of ice, or other forces not yet understood. Moreover, the mission could determine if dark comets are remnants of the early solar system, holding pristine material from its formation, or if they are fragments of collisions, shaped over billions of years through interactions with planets and other small bodies. Either outcome would significantly deepen our understanding of the diversity and evolution of solar system objects, revealing details that reshape long-held assumptions. Dark comets also challenge astronomers' observational methods. Traditional surveys focus on bright comets with tails and predictable asteroids, potentially missing objects that are dim, small, or moving in unusual ways. These bodies may be more numerous than initially believed, simply evading detection due to their subtle visibility and faint nature. Each new observation of a dark comet forces scientists to refine orbital models, develop improved detection techniques, and reconsider the dynamics of how small bodies move through space. Understanding these objects can improve predictions of their future paths, interactions with other celestial bodies, and potential encounters with Earth, making them important for both scientific knowledge and planetary defense. The potential hazard posed by dark comets, while currently uncertain, cannot be ignored. Their unpredictable trajectories and small, faint profiles make them harder to track than typical comets or asteroids. Even small deviations caused by non-gravitational forces could accumulate over time, altering their paths in ways that are difficult to predict with standard models. As such, monitoring these objects is essential for identifying any that could pose a threat to Earth, no matter how small. Planetary defense strategies may need to account for this previously underappreciated population, ensuring that humanity can detect, track, and, if necessary, mitigate potential collisions with these elusive, mysterious objects. Beyond the practical considerations, dark comets capture the imagination and spark curiosity about the nature of the universe. They remind us that our solar system is not a static or fully understood environment, but a dynamic and complex system where unusual objects can appear unexpectedly, sometimes originating from beyond our own star. Studying these bodies offers a rare glimpse into processes happening across the galaxy, potentially carrying material from distant star systems into our cosmic neighborhood. They also serve as a humbling reminder that the universe still holds countless mysteries, and that even within our own solar system, there remain objects whose behavior and composition challenge established scientific understanding. The more we learn about dark comets, the more we recognize the gaps in our knowledge about small solar system bodies. Their subtle accelerations, hybrid characteristics, and potential to carry water or organics make them a unique and valuable subject for scientific investigation. They blur the lines between traditional categories of asteroids and comets, prompting a re-evaluation of how we classify celestial objects and interpret their dynamics. Each new discovery adds a piece to a puzzle that may ultimately reveal new insights into the formation and evolution of the solar system, the delivery of life-essential compounds to planets, and the broader population of objects moving through interstellar space. Ultimately, dark comets represent both a scientific puzzle and an opportunity. Their strange behavior, subtle activity, and uncertain origins make them objects of intense study and fascination. Missions like the Japanese spacecraft targeting a dark comet in 2031 could provide crucial data, potentially transforming our understanding of these mysterious bodies. As astronomers continue to identify and observe these objects, we gain insight not only into the solar system's past, but also into the processes that shape planetary systems across the galaxy. While small, faint, and often elusive, dark comets carry immense scientific significance, bridging the gap between familiar celestial bodies and the unknown reaches of interstellar space. They challenge assumptions, expand our horizons, and remind us that even in our immediate cosmic neighborhood, there are secrets still waiting to be uncovered. By studying them, we not only learn about their composition and dynamics, but also gain a better understanding of the forces that govern planetary formation, the transport of water and organics, and the complex interactions that shape the evolution of the solar system as a whole. In this sense, dark comets are not just anomalies or curiosities. They are keys to unlocking some of the deepest and most fundamental mysteries about our place in the cosmos.